Welcome to this presentation on Magnetron Oscillator. Principle, Operation, Hull Cutoff and Pi Mode. Presented by Professor Gotapu Sasibhushan Rao. We will first look at microwave tube classification and the basic structure of a magnetron. Then we will discuss electron motion in crossed electric and magnetic fields, the Hull cutoff condition, RF field interaction, the formation of rotating electron spokes, and finally the important pi mode of operation. We will conclude with a numerical example on Hull cutoff voltage. Microwave tubes are broadly classified into two types: linear beam or O-type tubes and cross-field or M-type tubes. In O-type devices, the electric and magnetic fields are parallel. In M-type devices, they are perpendicular. The magnetron belongs to the M-type family, and this crossed field arrangement is the key to its operation. The magnetron is a high-power microwave oscillator. Here, the electric field and magnetic field are perpendicular to each other. Electrons emitted from the cathode move under the combined action of these crossed fields. Their interaction with the RF fields of the resonant cavities produces microwave oscillations. This figure shows the basic construction of a cavity magnetron. A cylindrical cathode is placed at the center, and the anode block surrounds it. Several resonant cavities are formed in the anode. The region between the cathode and anode is called the interaction space. The DC electric field is radial, while the magnetic field is directed along the axis of the tube. This slide shows different cavity geometries used in magnetrons. The common types are hole and slot, rising sun, slot, and vane structures. Although their shapes are different, all of them act as resonance structures. Their geometry influences the operating frequency, mode separation, and stability of the magnetron. Now consider the motion of an electron in the interaction space. The electron is influenced by both the electric field and the magnetic field. The electric field tends to move the electron toward the anode, while the magnetic field bends its path. Therefore, instead of moving directly from cathode to anode, the electron follows a curved or cycloidal type trajectory. The Hull cutoff condition gives the limiting combination of magnetic field and anode voltage. If the magnetic field is too high for a given anode voltage, the electron cannot reach the anode. Similarly, if the anode voltage is too low for a given magnetic field, the electron also cannot reach the anode. At the exact Hull cutoff condition, the electron trajectory just touches or grazes the anode surface. These figures show the RF field developed at the entrances of the resonant cavities. The RF electric field is strongly concentrated across these narrow gaps. Each cavity behaves like a microwave resonator. The alternating fields at these gaps interact with the moving electrons in the interaction space. This slide explains the main operating mechanism of the magnetron. The RF fields across the cavity gaps interact with the electron cloud. Because of this interaction, electrons do not remain uniformly distributed. Instead, they group together and form a rotating spoked wheel pattern, as shown in the figures. As these electron spokes move past the cavity gaps, they transfer energy to the RF fields of the resonators. This sustains microwave oscillation. The spokes rotate in synchronism with the RF wave around the anode structure. Finally, microwave power is taken out using an output coupling loop. For stable operation, the magnetron normally operates between the H3 potential and the Hull cutoff potential. The most important operating mode of a cavity magnetron is the pi mode. In this mode, the RF fields in two adjacent cavities differ in phase by pi radians, or 180 degrees. So, when one cavity gap has one polarity, the neighboring cavity gap has the opposite polarity. This phase relationship produces the desired rotating RF field in the interaction space. Conducting straps are connected to alternate anode segments to improve mode separation and stabilize the pi mode. Let us now apply the Hull cutoff equation to a numerical example. The cathode radius is 2.5 mm, the anode radius is 5 mm, and the magnetic flux density is 0.27 Tesla. We use the Hull cutoff voltage equation shown here. Here is the cathode radius is the anode radius is the magnetic flux density is the electron charge and is the electron mass. After substituting the given values, the Hull cutoff potential is approximately. So, for these dimensions and this magnetic field, the cutoff voltage of the magnetron is about 22.5 kilovolts.